Hey everyone, I am Dr. Surjit Singh. In this video on Python via examples, we shall talk about the quicksort method. Let us begin. In this session, we will learn about quicksort. It follows top-down recursive approach. However, it is not a stable sort. In this method, we carry out partition of the items of the list across a pivot item. We will discuss the difference between Lomuto and Hoare partition. We will compare its time and space complexities with other sorting methods. Quicksort is the fastest sorting method for arrays. It does in-place sorting, but it is not a stable sort. Like merge sort, this also follows the top-down divide and conquer approach. We are given a list for sorting. Unlike merge sort, where we do nothing during partitioning and sort the items during merging, in quicksort, we do all the work during partitioning and nothing during merging. Quicksort uses a recursive function sortRange which sorts items of the list within a specified subrange of the list. In the first call of sortRange, we fix start of the range to be 0 and end to be length of A. End is not included in a range, so in this initial call, we sort items from 0 to length minus 1, which means that we are sorting the entire list. We divide the range into two partitions around a pivot such that all items less than pivot move to its left partition while those greater than pivot move to its right partition. After partitioning, pivot is placed in between them. We then separately sort the two partitions recursively on the two sides of the pivot. If pivot is close to the median of the list, the two partitions will be of equal length and the process will be the fastest. But we cannot know the median of the list without sorting it, so choice of pivot needs some consideration. In case one of the two partitions get much less items than the other, number of recursive calls increases unnecessarily. Worst case is when one partition is empty and all the remaining n-1 items go to one side of the pivot. So choice of the pivot is very important. In a random list, any item of the list can serve as the pivot. So in Lomuto partition, we assume the first item of the list to be the pivot. In the present example, pivot is 3. 3 items of the list are less than pivot, while 6 of them are greater than pivot. But its worst cases in which the list is already sorted in the ascending or the descending order, or if all the items are equal. For such cases, Lomuto partition will give one partition to be empty while other having n-1 items, and in the next call of the function, we will have to sort n-1 items. Let us now learn about a better partitioning method called the Hoare partition. In this, we select a pivot randomly within the subrange in which we are sorting the list. Advantage of Hoare partition is that it uses a different random number in each call. So, if one partition is skewed, it will not repeat itself in other calls. Let us suppose that the random number between 0 and 9 turns out to be 3, where item 4 is present. This becomes the pivot. In order to separate it from the rest of the items, we swap it with the item at start of the range. We use this pivot to partition the rest of the list, for which we set up two pointers left and right at the two ends of the residual range of the items. Item at left is 1, which is less than pivot, that is 4. So it is rightly placed at the left partition. We leave it there and increase the left pointer by 1. Now that 6 is not less than pivot, it has to be moved to the right partition. So we hold the left pointer here for a while. Item at the right pointer is 7, which is greater than 4, so it is on the correct side of the partition. We decrease the right pointer by 1, but 4 is not greater than 4. Both 6 and 4 are on wrong sides, so we swap them and thus adjusting two items together to their correct sides in a single swap. After this, we move both left and right pointers together. Item at left is now 3, which is less than pivot. It is on the correct side, so we increase the left pointer to item 1 and then to item 4. We consider item equal to pivot as wrong on both partitions. Item at right pointer is 0. This is also on the wrong side of the partition. So we swap 4 with 0 and then move both the pointers. Item at left pointer is now 8, which is wrongly present at the left partition. So we check the right pointer. Same item 8 is correctly placed at the right partition, so we move the right pointer. Now that the two pointers have crossed each other, the partitioning is complete. The left pointer always stays at the first item that does not belong to the left partition, so the right partition range is known to us. As we have to place pivot between the two partitions, its position is left minus 1. Item present there belongs to the left partition, so we can safely swap it with the pivot that we have saved at start. Left partition items are from start to pivot minus 1. In the next call of the function sort range, we recursively sort the left partition and then the right partition. Lengths of the partitions decrease in every call. Ultimately, all recursions will reduce to the edge cases in which length of the range is either 0 or 1, which do not need any sorting. Quicksort is in-place sorting because items move within the area of the original range. However, it is not stable. Indiscriminate long-range movements of the items is the reason for this. We can verify this by analyzing the relative positions of 3 4s which have changed upon sorting. Let us now write the Python program for quicksort. We are given list A for which we call the function quicksort. Before using quicksort function, we must define it. We need random numbers in Hor's partition, so we import a random module before quicksort function. To sort items in a subrange of the list A, we define a recursive function sort range within the function quicksort. After defining it, the first executable statement of quicksort calls sort range for the entire range of the list A. Start becomes 0 and end becomes 10, the length of the list. End is not part of the range and sorting is for the entire range of the items from index 0 to index 9. Now we only have to develop the recursive function sort range. When range has 0 or 1 elements, we do not need any sorting. They become edge cases. In the Hor's partition, we find a random number within the range start and end. End is not part of the range. Let us suppose that the random number between 0 and 9 is 2 this time. We save it as R. Item at R is 6, which becomes pivot, and we exchange it with start. We now partition the remaining list into two parts for which we define left to be start plus 1 and right to be end minus 1. We continue in a loop while left is less than or equal to right. If item at left is less than pivot, it is already on the left side of the partition, so we move the left pointer. Items 3, 4, 1 and 4 are all less than pivot, but 8 is greater than pivot, so it is not part of the left partition, and we go to the else if part and compare the item at right pointer with the pivot. Item there is 7, which is greater than pivot, so we accept it there and decrease the right pointer. 4 is not greater than pivot, so it does not belong to the right partition. Now that both of the items 8 and 4 are on wrong sides, we reach the else part of the if statement where we swap them with each other and move both left and right pointers. 0 is less than pivot, so it belongs to the left partition and we increase the left pointer further by 1. Now that left pointer has crossed the right pointer, we come out of the while loop. Right partition starts from the left pointer. Left minus 1 becomes the pivot position. We swap the item there with the pivot present at start. All the items before the pivot are less than or equal to pivot. So we have parked the pivot at its proper position in the sorted list. We sort the items of the left partition by recursive calls of the function sort range and then the right partition by the same function. With this, we have sorted the entire range of the list. Memory used by call stack is of the order of log of n. In Hoare partition, the two partitions are nearly equal in length, so height of the partition tree is log n. We process n items at each level of the tree. Even if the partition is uneven in a call, it will not repeat itself in other calls because we get a new random number every time. We process n items at each level of the tree, so total time complexity is of the order of n log n. We do not copy a partition separately. Entire sorting is in place, so space complexity is log n due to the height of the call stack. In the worst case scenario, when partition is completely unbalanced, time complexity becomes n squared and the space complexity becomes n. Practically, when pivot is chosen randomly, worst case scenario does not happen, and for arrays, quicksort remains the best. We will now compare quicksort with other sorting methods. It is clear that quicksort is much faster than other methods, at least for large values of n. However, some overheads dominate if n is less than 60. As Hoare partition uses random numbers, the time of execution is not dependent on the distribution of the items in the original list. TimSort uses quicksort and then shifts to selection sort when in an iteration the size of the segment of the list goes below 60. Only restriction is that both quicksort and TimSort are not stable sorts. For stable sort, merge sort coupled with insertion sort remains the best. We know that log of 100 to the base 2 is 10, so it is worthwhile to look at the values of n log n against n squared. The table shows that for a million items, both quicksort and merge sort are 50,000 times faster than bubble sort, insertion sort, and selection sort, and for a billion items, they become 33 million times faster. In this session, we discussed quicksort method. It is a top-down recursive method. In this method, we carry out partition of items of a range of the list across a pivot item. We discussed the difference between Lomuto and Hoare partition. We discussed the time and space complexities and compared them with the other sorting methods. This method is the fastest sorting method but is not suitable if stability is an issue. Hope you enjoyed the video. Please feel free to ask for further clarifications on my email address given below. I'm looking forward to your comments. Please stay tuned for more.